we're going to start with one that we already know the answer of. I want to talk to you about finding the moment of inertia of a uniform rod of mass m and length L. So mass m and length L. I'm going to give you a set of instructions and steps on how to do this. And let me tell you, I will start out by reminding you that the actual formula we're going to use for moment of inertia looks like this. And it says to take each piece of mass, multiply by how far away it is from the axis of rotation squared, and do that until you've added up all of the mass. That's what this instruction says to do. So we have to find a way of turning this into something that is actionable, because this is not actionable, right? We don't know where every piece of mass is relative to the axis of rotation. So we have to come up with a way of writing that out mathematically, something that will give us a way to integrate. So I'm going to tell you from the very beginning, we are trying to integrate the shape of the object, not the mass. We know what the mass is. We want to integrate the shape. So we want to rewrite this in terms of something that has to do with the shape of the object. So step 1, identify a single piece of the object that you will use to represent any piece of the object. That sounds way more complicated than it is, but you're going to have to draw a square that represents a piece of the object. This is my piece. It is one piece of the object. Now, I think, because this object is very long compared to how wide it is, that I don't have to worry about how high or low this piece is. That the only thing that's really important about this piece is how far away it is from the end. Does that make sense? I'm saying this because we have to decide whether we're going to treat this as a linear object, an area of an object, or a volume. And I think we can treat this as a one-dimensional object, that it's more one-dimensional than anything else. Does that make sense to all of you? In the future, we'll have to do a disk. And a disk is clearly going to be two-dimensional. But I think this we can treat as a one-dimensional object. That it doesn't matter if the mass is up or down. It just matters how far away it is from the end. Everybody follow along? And trust me, we'll never do a volume. We will only do ones that are two-dimensional or one-dimensional. And the only two-dimensional we're going to do is the hoop and the disk. Does that make sense? So we're only going to see 4 of these, ultimately. So the next thing you have to do is we have to figure out a way of relating the shape of this object to its mass. Because the integration is about mass, but we want it to be about shape. So this next part is a little tough, so follow along. This is actually step 2. I need to find a way to point to each object that has mass. So I need to decide, how do I tell the calculus where each piece is? Since this is one-dimensional, I'm just going to use a one-dimensional variable. I think I can point to every piece of the object using nothing more than a distance. Does that make sense? Because it's one-dimensional. So in my head, I'm thinking the first piece is at 0, and the last piece is at L. And so x can be any number between 0 and L, because that's where every piece of my object is. Imagine this is a meter stick, and you're shaving off 1 millimeter pieces. Can you point to every single piece of a meter stick if it starts at one end and ends at the other? So I'm using x to represent a single piece. But I know that x will start at 0 and will go to L, because L is the last piece. Step 3. Can R be represented? R is the perpendicular distance from the axis of rotation to your piece of mass. Can R be represented using the variables you have just chosen? Now this one's one-dimensional, so the answer is of course yes. X is R. X does represent the perpendicular distance to each piece of mass. Again, for a one-dimensional one, some of these steps won't make much sense, but you have to imagine that it could be two-dimensional or three-dimensional. So I'll say it again. Can R, the perpendicular distance from the axis of rotation to your piece of mass, can R be represented using the variables you've chosen to point to the mass? And I would say yes, R equals X. X is our perpendicular distance. When we do the disk, it'll be more complicated than that. Next, define the size of your piece using the variable you created. I created X. I'm going to define my piece as being a little bit in the X direction. That's how I'm going to define my piece. That the size of my piece is a small bit of length. So I'm defining, I said that X is where the piece is, the size of it is a little more in the X direction. It's just defining how wide my piece is. Now, remember, this is linear, so all I need is a length. When we do a two-dimensional object, we'll need an area because it's going to define an area. We're going to be drawing a square. If it was three-dimensional, it would define a volume. Follow me? So for every type of thing, you would have to figure out whether it's a length, an area, or a volume. If it's one-dimensional, it's a length. Can I keep going? All right. This part's easy. We just need a ratio. You need to take the ratio of how much your piece weighs to how long your piece is and compare it to the actual ratio that was given at the start. What I mean by that is I'm looking at the density of my object. The density of the piece has to be the same as the density of the object, because I said I had a uniform density rod. Here's the caveat. So I just did a quick ratio here. You see that, right? The mass of a piece to the length of the piece equals the mass of the whole to the length of the whole. You follow so far? It's possible they could give you something that does not have a uniform density. Maybe something that gets heavier at one end compared to the other. They've done it once in 40 years. So again, don't do it. But if they do, they'll give you this. They'll give you the equation that tells you the density. They'll just give it to you. It'll be something with X in it, most likely. So don't fret too much, but at the same time, maybe just run away screaming and don't bother to do it. Okay? Because it can be hard. And I want to fool you that some of this stuff is really challenging. And it's only going to be worth a point or two, so it may not be worth investing in doing that. You follow what I'm trying to say? All right. Okay. Now, believe it or not, we're nearly done. I know it doesn't seem that way, but we're nearly done. You want to solve this for dm. So I'm just going to multiply both sides by dx. Okay. So we defined where the piece is, we defined the size of the piece, and now we've defined the density of the piece. That's what we've done. Where is it? How big is it? and what's its density. Our last step here really is to just assemble our integral. We're going to assemble the integral. We're going to replace all of these things with the stuff we've chosen to describe. So to assemble it, I'm going to replace r with the variable I'm using to point out each piece. That would be x squared. I'm going to replace dm with something that has to do with the object's size, not its mass. So that's this. I'm assembling the integral. I'm replacing what I have for r with how I'm pointing to the object, and I'm replacing what I have for dm with something that has to do with the size of the piece, not the mass of the piece. Everybody good so far? I need to tell it where the first piece is. And I need to tell it where the last piece is. Right? Because we're telling it where the first piece starts and where the last piece is. We're done. That's how you set up the integral. Now, setting up the integral, that's the part that no teacher ever tells anybody. They never tell them in school how to do this. I've sent dozens of kids to take physics. They never talk about this part. They just assume that because you've had calculus, you can set it up. No, calculus tells you what to do next. Like calculus will tell you how to do this. It doesn't tell you how to set up this integral. I will say that this integral is pretty straightforward. M and L are constants. They have nothing to do with where I am. M is the entire mass of the rod, L is the entire length of the rod, so every single part of my sum has the same M over L in it. So I'm going to factor that out. Okay, so this part, we've done this, right? I have x squared with respect to x, so I'm going to be using the polynomial function. I'm going to add 1 to x, to the exponent of x, and I'm going to divide by the new exponent. So I'll have x cubed divided by 3. That okay? Took the antiderivative, plugged in my limits. So now I have to apply my limits to this. So that'll be L cubed over 3 minus 0 cubed over 3. And one of the L's cancels. You guys see that, right? So I'll get 1/3 ml squared. We knew what the answer was supposed to be. Not terrible? I think this is actually some of the hardest stuff we do. It's not, it seems easy now when I'm here telling you what to put for this and what to put for that. But you can see how this can get hard pretty quick. So I want to prove something to you. I have 12 minutes. I think I can. Because what I have to show you next is us leaving one-dimensional problems and now talking about two-dimensional problems. But I don't think you're going to believe me. So I want to prove something that you already know. Can we do that together? Let's just say I have a disk, radius r, mass m. What's the area of a disk? The area of a disk? We're talking like, yeah, pi r squared. Good. I was hoping we'd get that one right. Good job. Area of a disk. Now, I bring this up because, although I have 12 minutes, you've never proven that. Somebody told you it was true, and you've believed them. What I want to do is I want to prove to you that the area of a disk is pi r squared. I want to do so because I want you to have a little faith in the process we're using. So here's what I want you to think about, because this is what we're going to do. We're going to, step one, choose a piece of your object. I'm going to choose a piece of my object. I'm going to draw a square that represents a piece of my object. This is our DM. Right? We did this just a minute ago, right? We talked about this. I'm choosing a piece. The second thing I said we had to do was define some variables to help us locate this piece. In the rod, starting from one end made perfect sense, but in the disk, we could start anywhere. So here's what I have to make some definitions. I'm going to say that I'm going to point to the first corner of my disk. But I need reference. So I'm going to say that right here, that's 0. And that I'm going over an angle theta and then going out a distance r. Right? Because this little square, I need something to represent where it is. Now, would you guys all agree that with r and theta, I could point to every single square in this disk? How many of you would agree with that? Because I could start at the center and go all the way out to the edge. I'll just go ahead and give us a value that the final one is r away, right? So I could start with this box here and do every box along 0, then go over and do every box along the next angle and go over and do every box along the next angle, right? But do you see how I could point to every single point on this disk if I just used r and theta? It's important for us to understand that if I'm going to do that, r would have to start at 0 and go to the capital R. And theta would have to start at 0 and go to 2 pi. Right, that way I can go all the way around the disk and start from the very center and go to the very edge. Now, your book does this different. If you want to see it done different, I encourage you to look at your book's treatment. I'm doing this purposely harder than your book. Your book does this as a series of concentric rings, which is easier, but it leaves out what I'm about to tell you, and what I'm about to tell you I think has value. In the last one, we said that we were going to look at the mass per unit length of our object, but this is a surface, right? This thing has area. So instead of looking at the length, I think I'm going to have to define the area of my little square. Does that make sense? An area is like base times height or length times width. Does that make sense? So I need to find a way to express this distance and express this distance so I can multiply them together to get dA, the area of my piece. You okay? Yeah. I think this part's easy, dr. Go out a distance r, then go a little bit more in the r direction. I think the other one, you're not going to believe me right away, but I'm going to say it anyways. R d theta. You know how a compass works, how you set the radius and you just do a little bit of an arc? Isn't that the same thing? I'm going out a distance r and then kind of sliding my pen over a little bit in d theta to get that length. I'm using actually this. That's what I'm using. And I'm saying that this little piece is about that long. D theta times R. You guys follow so far? It's just a little bit of arc length. Because I'm trying to define this. Because I want to do this times this as being the area of this piece. It's a length times a width. Now I know that this is like really a little bit of a curve, but you understand that the idea is it's so small you can't see the curviness of it. So dA is going to be dr times r d theta. And here's the thing. I don't think you guys have any idea if that's something to believe or not. So I want to prove this to you that this works. So here's how we're going to prove it. We're not going to find a moment of inertia of this thing right away. What we're going to do instead is I want to prove that if you add up every one of those pieces of area, you'll get pi r squared. That's what I want to prove. If I do that, will you believe that this will work as the area of our object? So let's prove it. Now you're not going to like this, I promise you, but it'll be okay. I'm going to replace dA with dr times r d theta, just like I said. But you'll notice there's two d things, right? There's dr and d theta. That means we have to do two sums. One for r and one for theta. I knew you wouldn't like it, but I don't really care. I have to add up both things. So just so you know, a double integral is just a thing. It's adding up two things at once. Triple integrals would probably be used for volumes, right? Double integrals would be used for areas. It's not crazy. And yeah, you get this in Calc 3, but it's not much. It's just a sum. And you're not going to have a problem with this because, can I finish? Because I only got 4 minutes. But r goes with dr, so I'm going to reorder these. I can multiply in any order I want. So I'm going to reorder them and put r dr times d theta. Remember before when we did stuff like this, r's had to go with the stuff that had dr, and thetas have to go with stuff that has d theta. That's how we separate our variables and collect like terms. We put the variables that we're going to integrate within the area of our integrating variable. Now, it's a sum, but it's two different sums. One is summing from the inside to the outside, and one is summing around in a circle. So I'm going to separate and do this as two separate things. Now, there's a reason we can do this and sometimes we can't. It'll never be the thing in this room that we can't do this. But if, say, the outer rings had more mass than the inner rings, like maybe it gets thicker towards the edge than the center, or say the reverse, maybe it was thicker in the middle than it is towards the edge. For example, Jupiter is thicker in the middle than the end. So if you want to do something like this for Jupiter, you have to take that into account. So when we try to get a theoretical idea of what's happening in Jupiter, we'll do integrations like this to deal with its density because it's more dense in the center than it is at the edge. But for us, we're just trying to figure out the area. And so I want to make sure I go from the first point to the last point in our circle. And I want to go from the inside to the outside of our circle. Now, we do these separate. So the first one is r with respect to r. That's a polynomial again, right? Add 1 to the exponent and divide by the new exponent. So that will be r squared over 2 from 0 to r. The next one, there's no number there, so you know that that's a 1, right? Which means theta to the 0 power, which means theta to the 1 power divided by 1, evaluated from 0 to 2 pi. my first term is going to be r squared over 2 minus 0. My second term will be 2 pi minus 0. So pi r squared, right? Just by adding up a whole bunch of little squares, pi r squared. Alrighty, bye.